Hello everyone, and thank you for joining us for today's webinar, which is titled Node Slope Analysis with LimitState GEO. I'm Tom Pritchard, the host for today's session, and I'll be introducing you to our speaker shortly and rounding up at the end. Hopefully today you'll come away with a good overview of how LimitState GEO's engineered element material works and how it can be applied to problems of nailed soil slopes as well as some other 1D reinforcement types. The webinar itself is going to run for approximately 45 minutes, and it will include at the end a few minutes for you to be able to ask your own questions. You can post these at any time during the webinar using the question functionality that should be present in the webinar interface, and we'll try and get round to them at the end. This isn't always possible, but we will try to reply to questions as well that we don't cover in the webinar via email over the next few days. So first off, I'd just like to introduce you to our speaker for today, who is Dr. Colin Smith, and he is the LimitState GEO Product Manager.
Okay, thank you very much, Tom, for that introduction. So, I'll just get this presentation. Okay, to start off, we'll look at a few slides showing the range of problem types that can be solved by LimitState GEO. As you're probably aware, LimitState GEO is a general-purpose ultimate limit-state software able to determine the collapse state for any problem geometry and able to model slopes, retaining walls, structural elements, and soil reinforcement, as shown by some of these examples. Our aim today is to focus on soil-nailed slope stability analysis. So in terms of the contents, we'll be looking at the 1D reinforcement modeling with the software, how it differs from other methods, and how to model some specific scenarios. We'll also take a quick look under the hood to see how the software works. So to this end, I'll primarily be using the software directly to illustrate the key points, but I'll make use of a few slides at the beginning and end for introduction and summary. And as this is a short presentation, the main aim is to give you a flavour of what the software can do, so there won't be time to get into all the details of the software functionality. However, as Tom has said, there'll be time at the end for questions. So before we look at the software itself, I'll first give you a little background to LimitState. Our mission is to provide engineers with powerful software for ultimate limit state analysis and design, leveraging the latest state-of-the-art algorithms and optimization technology. And this innovative approach has generated a client base covering over 30 countries worldwide. In terms of where our software fits, we focus on tools for ultimate limit state analysis, so it allows us to provide products that combine the speed, ease of use, and simplicity of traditional methods, but also give us the flexibility of finite element methods to handle any geometry. So thus, the only parameters we really need are the cohesion, friction, and self-weight of soil, plus properties of any other materials that we will incorporate into the model. So, basically, the software sits in the middle between traditional approaches, which are fast but somewhat limited in the range of problems they can deal with, and nonlinear finite elements, which are extremely flexible in what they can model, but often take much longer to use and a degree of expertise in use. So, that's enough introduction. Let's look at reinforced soils. So in terms of soil reinforcement that we might wish to model, the purpose of the reinforcement is to essentially add tensile strength to the soil, or equivalently transmit load from one part of the soil body to another via tensile forces. And this reinforcement might be one-dimensional or two-dimensional, so it could be soil nails or steel strips in the one-dimensional category, geogrids and geotextiles in the two-dimensional category. Now, the software LimitState GEO is a two-dimensional program, so it can model two-dimensional reinforcement directly, but we need a special approach in order to be able to model a one-dimensional reinforcement in such a way that soil can be modeled to flow past the reinforcement element if needed, but the reinforcing element can still provide that reinforcing action on the soil body. So we've got a few illustrations here of the range of models that you can look at. So a reinforced slope, a reinforced soil wall, or a reinforced embankment. And of course there are many more applications that can be modeled using the software. Now we're going to focus on slope analysis in this webinar. So in terms of analysis, if we examine standard textbooks and design codes, we can see a broad consensus on the general principles of modeling reinforcement. For slope stability, often we'll be using conventional slope stability methods, such as method of slices or a wedge analysis type approach. And in those, we assume a slip surface shape. And if we've got reinforcement within our slope, so down here, for failure to occur, the reinforcement must pull out of the sliding mass or the stationary soil mass, depending on relative length of reinforcement either side of the slip surface. So if we know what the shear resistance is around the reinforcement, we can calculate the pull-out force, and then that force can be applied in our slip circle analysis, enhancing stability. And determining this pull-out force is a key part of the analysis, and we can determine those by different methods. Now, while the method of slices is commonly used, it requires a number of assumptions, whereas LimitState GEO uses a very different approach which avoids assumptions and can determine the critical failure mode regardless of the geometry, but still models the same underlying principles of reinforcement action. And to some extent, you can imagine that the analysis at LimitState GEO is like a wedge analysis, except modeling one wedge, we're modeling thousands and thousands of wedges. So wedge analysis is the other common method of analyzing reinforced slopes. And it's the same principle. You've got a predefined slip surface and you're looking at a length of reinforcement, for example, here, outside and inside, calculating the restraining force and applying that to the wedge analysis. So those are the broad principles of how we would include reinforcement in stability analysis. And as I said, LimitState GEO takes the same approach. Before we go and look at some details, we'll just look in detail at how the software works. So the software uses a solution technology called discontinuity layout optimization, and this can be used to provide rigorous upper bound plasticity solutions. It's a rapid and direct means of analyzing the collapse state. It's the outcome of EPSRC project carried out at the University of Sheffield, and the first publication outlining this new method was published in 2007 in the Proceedings of the Royal Society. Now, the way the core method is formulated is a simple linear optimization problem, and it's quite easy to describe it. So just go through the principle here before we talk about how we include reinforcement in this type of analysis. So we have, in this diagram, a little block of soil with supports to the left and the base, and a load above. We discretize the block of soil using nodes. So rather than elements, which is used in finite elements, we populate the domain with nodes. So here we've got 3 by 4, so that's 12 nodes. And we connect every node to every other node to give us a range of potential slip lines that could form a mechanism of failure. So if we've got 12 nodes, we've got 12 times 11 over 2, 66 possible connections. And having set up all these possible connections, we then feed the problem into an optimizer to pick out the connections that will generate the collapse mechanism that dissipates the least energy. And so out of those 66, we're down to 6 discontinuities that in this very simple case form the critical collapse mechanism. Now, generally, we don't work with 12 nodes. Software will work with 500, 1,000, 2,000 nodes and be able to produce an accurate collapse mechanism. And the more nodes you put in, the greater the accuracy. Now, when the software identifies these slipline mechanisms, as you can see here, it will animate them to help interpretation. And in this particular diagram, we can see how that also works with a reinforced wall model. So this green line here is, for example, a reinforcing strip. and in this case it's attached to a facing block. That facing block is moving out, and so you can see here that the reinforcement is being pulled out of this stationary block of soil at the back. Here we've set it up so that there is a rather weak link here with the facing block, so in this case the reinforcement stays where it is and the facing block is pulling out of the reinforcement as this wedge slides down. So the software is flexible enough to model a range of different interactions by way of its formulation, and we'll have a look at that in just a moment. In terms of verification, the software has been verified against a wide range of closed forms and solutions and benchmarks, several thousand that are automatically run every time the software is changed. Over 100 of these results can be viewed on our website. I'll just put one diagram here from a paper which shows a comparison of the DLO LimitState geoanalysis against some results in the literature. There isn't time to go into the problem in detail, but you can see a good correlation in terms of how that fits. And you can also find on our website a bibliography if you're interested, so where we've listed all the papers that have been written using the software broken down into different categories. So here's just an extract of the papers that have been written looking at reinforced soil. So let's look back at how we model one-dimensional reinforcement. So for undrained soils, we would assume the shear stress at failure of the reinforcement boundary is alpha Cu, where alpha is an adhesion factor. And then if we know the diameter or the circumference of the reinforcement, then we can calculate the pull-out force. So if we have a diameter d, then pi d times alpha Cu will be the pull-out force of that reinforcement per unit length of reinforcement. And we also have to specify that per unit width into the diagram, remembering that the software is plane strain software, but these one-dimensional elements will be distributed at a particular spacing into the diagram. So that's the cohesive soil, and what we'll do is just have a little look at the software now. Just run that model there. So we have a little model here set up just to illustrate the principles of how this works. So I'll just run through these briefly. So what we have here is a block of soil, which we can just look at the properties of. So in terms of how the software screen is set up, we have the main viewer at the center, materials that we can use highlighted on the left, a number of buttons to the top and the left to define the problem geometry and solve the problem. And on the right, we have what's called a property editor. Anything I click on in the main window, its properties will appear on the right. So if I click on the soil here and here, I can see that it's a material, which is a soft clay, which is defined to be, let's have a look, it's got an undrained strength of 30. That's the most relevant property for us at the moment. And embedded in that is a reinforcing element, what we call an engineered element in the software, and this is, if I click on that, it appears up here, its properties, and it's called reinforcement element R2. And what we've done is essentially we've defined a pull-out factor of 10 here. So that is that on that previous slide, that's that value TC that we just calculated. So it's the circumference of the nail multiplied by alpha multiplied by Cu. So that corresponds, so if the undrained shear strength is 30, then approximately it corresponds to a 10 centimeter diameter nail spaced at 1 meter intervals into the diagram. The nail itself, if I clicked on it, I can also see its geometry down here, and I can see that it starts from x equals 2, goes on to x equals 4, so it's 2 meters long. And so we would expect to pull that nail out of the soil. We've got 2 meter length, and we have to multiply by this pull-out factor 10 kilonewtons per meter length per meter width. in order to do that, I've just modeled a rigid block here. So these are fully rigid blocks to which I can apply a force, and I've embedded the reinforcement into that block. And I've got another block of reinforcement here, which has different properties, called it R1. And here I've put the pull-out factor to be effectively infinity. So it is basically locked into this block here. And then I've put between the block and the soil another material called a no-tension cutoff material, which basically allows the two blocks to pull apart without any resisting tensile force. So to solve the problem, I simply click this Solve button. The software will do a quick diagnosis of the problem and flag up any attributes of the problem. It's given me a warning which we'll ignore, but it's basically saying the reinforcement element has reached the back boundary, a fixed boundary here, and it's just highlighting the fact that that does not automatically mean that that element fixes into the back boundary. There are ways of doing that, but it's just a warning in case the user thought that that was how that particular attribute is modeled. So we just click OK on that, and the software quickly derives the number. It's a very simple failure mechanism. Essentially this block pulls out and it displays the axial force building up in that reinforcing element up to here. So obviously it starts at 0 at this end and it builds up to a stress of 20. And that's what we're expecting. That 2 meters times that TC value of 10 gives us a pull-out force of 20. And this is essentially the load that we are given here. So that reinforcement pulls out with a value of 20. Now, just to show you how that works, if I click on this again and I double that factor to 20, then I would expect to get a pull-out force of 40. I'll ignore that warning. And again, yes, I get 40. Now, I can access material properties by clicking on elements here and looking at the materials that are within them, or I can directly look at materials on here. So we know that the reinforcing element, the soil nail we're modeling, we've called it R2. I can directly access those properties here. So that's an alternative way of doing it. And what I'm going to do is increase that 20 to 100. So we would expect to get an answer of 200, but if I solve the problem, we see that I get an answer of 120. And that might seem counterintuitive, but we have to remember that that TC value, that value that we've defined here, effectively relates to the size of a soil nail. And because we're now on 100, we're now modeling a very large diameter soil nail. And actually, it's becoming so large that we put a number in that is beyond the geometry that we've actually specified. It's actually giving us a pull-out strength that is bigger than a sheet of reinforcement would provide in that place. Therefore, the software will limit that value to the largest credible value, which is if that reinforcement was a sheet, a 1 meter per unit meter into the diagram, and that has limited us to the value of 120, which basically equals that value of the shear strength of the soil here. If I just unlock that. So if you remember, the clay had a shear strength of 30. If it was modelled as a sheet, we have to multiply by 2 for the top and the bottom surface of the sheet, and then multiply by the length of the element 2. So it's 30 times 2 times 2, which gives us a 120. So the software will automatically limit that value. What I'll finally do is set a rupture strength here. We'll come back to this a little later. And that is a limiting value on the tensile force within the reinforcement. So if I set that to 60, at the moment it was set to infinity, then it basically says the reinforcement cannot get up to a tensile force larger than 60. So we can see that the load down here is now coming out at 60, and the force is simply building up to that value of 60. And what essentially is happening, if I click this animation again, is the software is basically modelling the reinforcing and failing in a ductile way. It's stretching once it gets up to that value of 60. Okay, so that's looking at reinforcement interaction with a cohesive material, or if there is a cohesive element in the strength property. If we now go back to the presentation, so I'll just shrink that down. More often we're going to be concerned with frictional or effective stress parameters, so often we would assume that the shear stress at failure on the reinforcement boundary is going to be alpha, this adhesion factor, multiplied by the normal stress on the reinforcement multiplied by tan phi. Now, often it's quite hard to work out what the normal stress is on, say, a soil nail, so in the literature you can find various factors for converting the vertical stress, which is easier to calculate, into the normal stress, so we're just going to call it K. There isn't time to go into the details of that. And so for a 1D cylindrical reinforcement, we're going to end up with the pull-out force per unit length and per unit width is the circumference of the reinforcement times alpha times tan phi times K times the average vertical stress acting along the length of the, or per unit length, a unit length of the reinforcement. So actually, yeah, we'll go back to the software first and illustrate that. So here I've got a very similar model, but slightly different from the previous one. So I've got this same block here where we're pulling the reinforcement out. This time I've got sand modelled as a soil, so we've got a granular fill. It's modelled with a 30-degree angle of friction, but the key parameter here is a unit weight of 16. We still have our reinforcement element sitting in there. If I click on that, now we've just expand this detail a wee bit. This value of TC I've changed to 0, and I've set this value TQ equals to 1. So that's a value we just looked at on the previous slide. The TQ is multiplied by the average vertical stress acting on the reinforcement, and that gives us the overall resistance. I've also slightly modified the problem to put these rigid blocks here. That is essentially, as when we pull this block away, we don't want the sand just to fall out, so I've just put some rigid blocks here which are fixed to fixed boundaries here, and I've put this no tension cutoff element here so that this block can pull away from this wall. So what we would expect is, looking at this block, its geometry, it goes from 3.5 to 4, so it's just half a meter of soil. The soil had a unit weight of 16, so the effective stress, it's just dry soil, the effective stress there should be 8, and that's got to be multiplied by our coefficient TQ, which is 1 in this case, so 8 times 1, but then we've got a length of 2 meters. So we should hopefully see a value of 16 as the result, and again we can see the tensile stresses building up along the reinforcement. Now I should have also mentioned that we've modelled this little length of reinforcement again in a different way to allow it to pull through this rigid block. If we just have a look at that, call that R1A, and effectively I've set all these parameters TC and TQ to 0, so that means I have no shear interaction with the surrounding material, and so they're just free to pull through completely. Just to wrap up that little explanation, the force is calculated based on the ambient vertical stress, or the initial vertical stresses acting on the reinforcement. So if I were to increase the height of this level here, so what I've done is I've clicked on this corner, I can see its coordinates are there, 4 and 4.5, 4 and 4, sorry. I can edit that value, make that 4.5, hit return, and apply that, and I've now put in a slope. So if I then solve that, you can see that I get pull out again, but now the value's gone up to 24, and that's because we've now got this inclined slope here, so the average depth of soil is now 0.75 meters rather than half a meter, therefore we've increased the pull-out load by 50%. So hopefully that's given you an illustration of how the key parameters of pull-out are determined, are used in the software. I jump back to this diagram here. So to summarize, we can see that the pull-out force on any reinforcing element is going to be its circumferential area, its length, alpha times k times sigma b times tan phi for the frictional element, and alpha cu if we have a cu term in there, or alpha c dashed for effective stress for the cohesive element. And what we do is reduce that equation down to this in the software, so it's the length times tq times sigma v plus tc, and it's up to the user to specify the value tq and tc, which are going to come out as alpha k tan phi for tq and alpha cu or alpha c dashed for tc, and then the software will model that interaction correctly, or in line with the way it's done conventionally. There are other parameters that we can use in the software. I'm not going to go into them in great detail, as well as if a block of soil slides past some reinforcement, it will have a shear component and a normal component of movement. In conventional calculations, we only are concerned with the shear component, and generally the normal component of resistance is ignored. But there are parameters called N in the software which you can set if you wish, but we're generally going to keep those at 0. And as I illustrated earlier on, if we have a tensile force acting in the reinforcement, we can put a limiting value on that by setting this parameter R, such that the reinforcement will fail if we get to that stress level. Okay, so having looked at the underlying principles of how those reinforcing elements work, we'll look at an example, saw-nail reinforced slope. So this is taken from a paper by Clark et al. In 2013. Effectively, we've got some soil nails of diameter 0.25 meters. We're going to assume full interaction, alpha equals 1, that they're spaced at a 1 meter intervals, and the soil properties are, we've got a C dashed of 3.5 and a phi dashed of 26. So the parameters we have to feed into the software, as I mentioned earlier, we have to calculate those. We have a TC value, which is pi d times alpha C dashed divided by the spacing, and that comes out as 2.74 kilonewtons per meter, and a TQ value, which is pi d alpha tan phi over n, which is 0.383. And here I'm assuming that that K value that converts vertical stress to normal stress is just 1. But we may have a slightly different value in that case. So effectively, we're just going to use 5 of these nails, a very simple configuration to reinforce this slope. And I'll just open up that model. So there it is in the software. And we'll just have a look at the nail properties. So you can see that TC value of 2.74 and that pull-out factor of 0.383. These lateral factors N, which relate to movement of soil normal to reinforcement, as I said, are normally set to be 0. I've just set one of the values to just slightly above 0. This is because if you set them fully to 0, sometimes you find that the simplest mode of failure is for the reinforcement to float vertically out of the soil because there is no resistance modelled. So we put a little nominal value in there just to prevent that. And I'm modelling the resistance as it's a fully rigid or nail. Now we could put those nails in perpendicular to slope. They've been put in horizontal here, but there's no reason why we can't change the geometry. I mean, I could do it like that if I wanted, or you can draw the geometry in another way, or import it from a CAD file. We have buttons redo and undo here, so I'm just going to undo that and set that back to where it was beforehand. So again, if I click that, that just gives us the full view of the problem. All I will need to do to solve the problem, so we'll look at soil A first. So there we can see the soil has a C dash of 3.5, 526, and we've specified a unit weight of 17. So if I click solve, the software will very rapidly work out the failure mechanism, and basically it's finding the most efficient way to deform the soil between the reinforcement. And in this particular case, it's finding essentially a shallow failure adjacent to the slope face. More conventional analysis might consider two wedges further back, but these would be less critical for this particular parameter set. Now, I haven't explained fully what this solution means. So we get a solution here which is called 1. And if I click on this solution, it tells me the definition. So the software is able to solve problems in two different ways. But if we're modeling, for example, a slope, generally, in many cases, it's going to be stable. So we have to drive the slope to failure by some way analytically. We can either do that by reducing the strength of the soil, or we can increase the weight of the materials in the slope, and that's what we've done in this case. We're using what's called a factor load mode, and what we've done is we've said that all the soil in the problem, we have to increase their weight in order to cause the system to collapse. And if I click on these objects, you can see that we've specified essentially all of the blocks. Now we've just got a factor just over 1, so it's saying that this problem is pretty much on the limit. It's just about to fail, and if we increase the unit weight of the soil from 17 to this value here, we would get failure for this particular mode. And that's essentially how the software is calculating its failure. Now, if I shorten these nails, then what we'd probably get is find that the nails were not reinforcing the larger body of the slope, and that we might get failure behind the nails. So if the nails don't have sufficient length, then we're going to get a problem. So I'm going to do this just by clicking on the slope. So it's a bit rough and ready. I'm not making sure that we're keeping these nails horizontal just for speed, but it is relatively easy to do that. But hopefully this gives you an idea that I can play around with the geometry of this problem quite quickly. So the software is very good for doing what-if type calculations. Just see what happens if I shorten those. So if I click solve again, hopefully I've got them about right. So you can see now that the failure mechanism is essentially, the critical one is now outside the reinforced area, as we would expect. And this is behaving, still deforming slightly, but we're getting a major slip plane around the back and then diving between these two reinforcing elements. And we've got a much reduced capacity. So now what the software is saying is that for this slope to be stable, it would only be stable if the unit weight of the soil was 8.2 rather than 17. So it's basically got a factor of 2, well, a factor of a half on the factor of safety on weight of material. So it's definitely unstable, as we would expect. And what you can do in the analysis is, let me just click on that. If I click on the reinforcing elements, I can see the stresses that are building up within those elements. So you can see that they are starting at 0 at one end, climbing, and then falling back to 0. And if you hover over any of those elements, it will tell you what the current axial force is there, the shear force, and the moment. In this particular case, because we're modeling rigid reinforcement, it doesn't actually calculate the moments, and that's why it says unavailable. But if we gave the nails an actual bending strength, then that would be calculated. Okay, so we jump back to the presentation. So we're coming towards the end of the presentation. That particular model was looked at in the paper by Clark et al. And compared that with a two-wedge mechanism and forced the software to also adopt a two-wedge mechanism rather than the critical mechanism. And you can see from this graph that there's perfect match between the two-wedge model and the software when it's been forced to emulate a two-wedge failure mode. If the software is allowed to find the critical failure mode, then of course it finds lower factors of safety because it's not constrained to just one particular type of failure mode. So to summarize, the implementation of reinforcement elements in LimitState GEO allows soil to flow past reinforcement. It's been calibrated against two-edge analysis and many other analyses. And when modeling the 1D reinforcements such as soil nails, what we've called the engineered elements within the software that we use to represent reinforcement, we have to, as you've seen, hopefully you have to calculate TC and TQ based on the nail geometry and the soil properties. The lateral coefficients typically set to 0. We may wish to specify a rupture strength in the nail to allow for failure. And there is also a provision in the software, I didn't really go into it, to define boundary materials on the reinforcement. That's not really relevant for a one-dimensional reinforcement and is more relevant when we're modeling two-dimensional reinforcement. So we don't do that. So, in conclusion, reinforcement modeling in LimitState GEO uses the same mechanics as conventional methods, such as a two-edge method. All the equations and mechanics are essentially the same, but they're set up in such a way that we can model thousands of wedges in order to capture the most critical mechanism, and with no need to identify internal or external failure in this type of analysis. It's all handled inherently by that interaction model, how the engineered element interacts with the soil. So we don't need to worry about pull-out lengths or reinforcement rupture. That is all inherently captured within the software. And we automatically search all possible failure modes every time it's solved, so that you will always get the most critical failure mode. I've shown you briefly how we use the software. Haven't had time to go into that in full detail, but hopefully you can see that the workflow is quite straightforward. We can solve with one mouse click, we can play around with the geometry, look at properties of materials, edit them very easily. Didn't have time to look at partial factor application, but the software is designed to allow application of Eurocode partial factors. So with such an interactive interface, it's a very useful tool to answer what-if type questions, just to get a feel for a problem, what's important, what's less important in that problem. And while we've only been looking at slope problems here and pull out of reinforcement, the software can solve any problem type, as you will have seen in those first few slides of all the different solutions, so retaining walls, foundations, slopes, etc. So, thank you very much for listening. I'll wrap up there and pass back to my colleague Tom.
Thanks, Colin. So we've got a bit of time left at the end here just for any questions. I will have a look and see whether anybody has posted a few. If they have, then we'll try and get around to them. If you have one that you'd like to ask, then do type it into the question box now and we will try and answer it for you. Okay, I think we've got a few coming through, and I'll let Colin answer them as they come in.
Okay, so I had a question about the nails always ending at a boundary. Why is this? So if I bring up the software, let's just look at this one again. So the nail here is essentially modelled on a boundary, and the boundary itself cannot end in the middle of a solid block, so it has to be connected to another boundary. So the way the software works is that soil nails are applied to boundaries, so must be modelled on boundaries, and because those boundaries must always meet other boundaries, that's why you have to have a boundary there, rather than these items being missing. So they don't make very minor difference to the analysis having this boundary in, but it is necessary to draw that in. So if I wanted to extend that nail, for example, from here, but only part way to say to there, I could do it in two ways. I could either do what I've done over here, or I can go all the way to that end and then add a vertex part way through, and then take this nail. I can use drag and drop in the software and drop that there, and now I've extended the nail all the way through to this point. So it's still connected to a boundary here, but this boundary effectively is just modelling the soil here, but this boundary is modelling now the reinforcement. Probably won't make much difference to the analysis because we're getting a local failure on the face, so this extra level of reinforcement makes very little difference to the failure that we're getting. Got a question about how we generated the models. Did we draw them by hand? So there are various ways of doing that. If they're fairly simple, we've drawn them by hand, but you can draw them in a CAD package, and we have the facility, if I just show you here briefly, to import a geometry. I haven't got any in here at the moment, but we can import DXF files, and therefore for complicated geometries we'd recommend you did that, generated them in a CAD program and imported them. We also have a number of wizards for a lot of standard problems built into the software, so you can very rapidly build a conventional geometry. So for example, a reinforced soil wall here, we can very rapidly define the geometry through a number of parameters, and it will automatically build a model for you. Won't go through that in great detail, but you essentially add soil properties and geometry properties, various partial factors, and then it essentially draws that geometry for you. So there are various ways of producing that. Okay, so I've got a question. Is it possible to put soil nails through a masonry wall? So if I zoom in here, I guess effectively you can imagine these are masonry blocks. These are actually concrete facing panels in this particular model. So the nail is where it passes through the concrete block. In this particular model, we've modeled its properties as having a pull-out factor of essentially infinity and a lateral factor of infinity, which means it's locked into that block. If you want to pass it through a block but not actually have any shear interface with that block, then you can reduce the pull-out force to 0. If there's going to be some interaction, then you can set these parameters as appropriate. So it's very much you've got the control to set how the nail passes through different materials as you like. Again, you have to remember you are idealizing this kind of one-dimensional nail into a two-dimensional piece of software. I've got a question about, can I elaborate about the bending behavior of the nail? So if I just run that model, so we get a multiple wedge failure mode for this particular block, and what we can do is see the axial forces building up along that. Now if I just look at the resistance, this reinforcement has been modeled with 0 moment of resistance here, so I get 0 moment, which basically means that it's effectively allowed to bend as we get deformation. And actually, if I click on the animate button, we may see that. Yeah, you can see it slightly deflecting here and here as the wedges deform around it. Now, if I wanted the reinforcement to remain as fully rigid, I can set this moment of resistance. I'll set it to something quite high, like 1,000, and then solve. It probably won't make a huge difference to the collapse mode or collapse force. It's made very little difference in this particular case because there wasn't a lot of flexing. I can actually choose what is displayed here. I'm going to display the moment. So these are the moments that are building up, and they're actually building up to very low values in this particular case. If that moment had built up to a value that exceeded this number that I put in here, then we would get bending of the nail. So essentially, these engineered elements will along their length we calculate the moment of resistance in the analysis, and if that moment of resistance that bending moment exceeds the specified moment of resistance, then that engineered element is free to bend at that particular location. I think it's possibly easiest to illustrate that with a sheet power wall model. I'm just going to put some sand in here. So here we're using the engineered elements. This is the same element we can use to model a soil nail. We're using it actually to model a sheet power wall, steel sheet power wall. And in this particular case, I'm going to put in a low, I'll put in something like 50 here for the bending. And if I solve the problem, what happens? Okay, I think the stress levels, 50 is not quite low enough. It's basically deforming as a rigid body, but if I give the sheet power wall a very low bending strength like 10, we get essentially it just bends at this point. So that's the same sort of thing that could be modelled in a soil nail if so desired. Okay. So question, where in the software can I see the nail itself hasn't ruptured? So again, that's primarily, if I go back to this model here. So you can see that in the animation, but also if you look at the graphs of the axial forces within the nails, you can see where if they flatten off, they're effectively hitting the rupture value. But you can look at the values and compare those with the specified rupture strength. Now, when you're using the software, rather than looking at what the axial force that is predicted by the software, it's much better. You get the most power out of using the software by actually specifying the limiting axial force or tensile resistance of the material and seeing whether the resulting analysis is stable or unstable. And that's a better way round of using the software. Right, we're slightly running over time here, so I will answer one more question and then so we had a question, can we model piles? So the answer is you can essentially use these. Imagine a pile is like a very large diameter soil nail, so it is possible to model piles this way. Generally, piles that might be used to reinforce a slope. So rather than piles to take a load from a structure, And then if you're reinforcing a slope, again, you can just calculate in the same way the resistance to soil moving past the pile. And this is where I think these lateral values would start to become significant, because that's the main purpose of a pile that's used to reinforce a slope, that you're looking at the lateral resistance. So you can represent those piles by these one-dimensional elements and still get the two-dimensional slope stability analysis. Okay, well, there are a few more questions there, but I'm afraid we're out of time, so we will get back to you on those, but I will pass back to my colleague Tom just to wrap up, and thank you very much for your attention.
Thanks, Colin, and thanks to everybody for joining us today, and hope you found the webinar informative and learnt some stuff. As we mentioned at the start, if it's prompted any questions, in addition to the ones that we've already answered, then please do get in touch via support@LimitState.com, and we'll be happy to answer those questions for you. We will also get round to the sort of 3 or 4 questions that we didn't manage to answer during the webinar today. If you'd like to watch the webinar again, or if you think you might know somebody who'd be interested to see it, we will be making a recording available over the next few days, and there'll be an email going out with a link to our YouTube channel just to point you in the right direction. Please also do look out for event notifications for other webinars and events that we'll be holding. They'll go out via email and also posted on our website, which is LimitState.com. So just finally, I'd like to say thanks again to everybody for listening, and we do hope that you can join us again for one of our future sessions. Goodbye.